Hey there. Today, we're going to pull back the curtain on one of the most powerful technologies out there, machine learning. We're going to take a journey to see how a computer can actually learn, almost like a person, to make these incredibly important predictions, like, say, detecting a disease just from looking at medical data. So, let's get into it and see exactly how it's done step by step. It all kicks off with something you deal with every single day. That spam filter in your email, that's a perfect, everyday example of machine learning. Nobody sat down and wrote millions of specific rules for what a spam email looks like. Instead, the system just learned by looking at tons and tons of examples of what is spam and what isn't, and it figured out the patterns all on its own. And right there, that's the absolute core idea. Machine learning is all about letting a system learn from a big pile of examples, what we call a training set. So instead of a developer writing a million rigid if-then rules, we just show the machine what we want the outcome to look like and let it figure out how to get there. All right, let's dive in. Let's start that journey from raw examples to powerful predictions. We're going to see how one of these models gets built from the ground up. And you know what? That process always starts with the most important ingredient, the data itself. So, here's something that might surprise you. Every machine learning project, it doesn't start with some super complex algorithm. Nope, it starts with a little detective work. The very first step is to really dig in and understand the raw material we're working with. Yeah, because data almost never shows up in a nice, neat little box. It's usually this chaotic mess of numbers and text. It really needs that human touch. Someone to sift through the chaos and start finding the hidden stories inside. Take a look at this. This is a plot of some housing data from California, where each dot is a different district. I mean, right now, it's just a big cloud of dots, right? Kinda useless. If this were our medical data, with each dot being a patient, we wouldn't be seeing any clear patterns here at all. Okay, now check this out. And here's the wild part. This is the exact same data. All we've done is change how we're looking at it, making the dots a little transparent. And suddenly, boom, the patterns just leap off the screen. You can see the big population centers clear as day. It's a perfect example of how just shifting your perspective can reveal everything. And that really gets to the heart of it. This whole first phase of exploration isn't just about making cool-looking charts. It's about building a gut feeling, an intuition for the data. This is the foundation we need to build a model that actually, works. Okay, so we've played detective, we've found some clues in our data. Now it's time to actually build this thing. The next big step is to carefully prepare our data so a machine, which, remember, really only gets numbers, can make sense of it all. Now, this involves a few really crucial steps. First up is data cleaning. You gotta fix errors, fill in missing blanks. Then there's feature engineering, which sounds fancy, but it's just creating smarter data. Like, instead of just using height and weight, you combine them to create BMI, which is way more useful. And finally, feature scaling, which just puts all the numbers on the same scale so the model doesn't get confused and think one thing is more important, just because it's a bigger number. All right, our data is prepped and ready to go. Now we get to pick our tool for the job. And for what we're doing, predicting if a tumor is malignant or not, there's a fantastic, super common choice called Logistic Regression. And what this model does is actually pretty straightforward, which is what makes it so cool. It takes in all that patient data we prepared, and it spits out just one number, a probability, somewhere between 0 and 1. A number near 0 means, nah, probably not. A number close to 1 means, yeah, very likely. Simple as that. So, you might be wondering, how does it make sure its answer is always a probability between 0 and 1? Well, the secret sauce is this beautiful S-shaped curve you see right here. This is called the Sigmoid Function, and it's basically the mathematical engine at the very heart of our model. So, here's the key takeaway. It doesn't matter what crazy number the model spits out internally, big, small, negative, whatever. The sigmoid function acts like a little compressor. It takes that number and just squishes it down, so it always fits perfectly on a scale from 0 to 1. It's the perfect translator to turn raw math into a clean probability. Okay, so we've got our model trained. We should be done, right? Well, not so fast. This is where we run into one of the single biggest dangers in all of machine learning. We have to make sure our model has actually learned the rules and not just memorized the answers. Think of it like this. You've got a student who just memorizes the answers for a practice test. I mean, they'll get a perfect score on that specific test, for sure. But then they'll completely bomb the final exam because they never actually learned the concepts. We have to make sure our model isn't that student. Just look at that dotted blue line on the chart. See how it's twisting and turning, desperately trying to hit every single blue dot? It's not learning the pattern, it's memorizing the noise. And when it sees new data, those red squares, it gets it totally wrong. This is called overfitting. But now, look at that solid blue line. See how it kind of ignores the outliers and just captures the general vibe, the main trend? It's not perfect on the training data, but because of that, it does a much, much better job predicting the new red squares. We get this better model through a process called regularization. So let's boil it down. An overfit model looks brilliant on the data it already knows, but it's totally useless on anything new. And that leads us to the final and maybe most important part of the whole process. Because building the model, that's not the end of the story. It's really just the beginning of a whole new journey. Why? Because the real world doesn't stand still, right? People change, environments change, and the data coming in today might look totally different from the data we trained on. This is called data drift. So a model that was a genius last year could be completely wrong today. Launching is just step one. So keeping a model healthy means putting it on a continuous cycle. You have to keep collecting fresh data, you have to watch its performance live, you need systems to spot when things go wrong or when that data drift happens, and you have to retrain it regularly with new information. And ideally, you automate that whole thing. And after all of that work, this is what success can look like. Let's say our cancer detection model hits 95% accuracy. That's incredible. That can literally save lives. But we can never, ever forget about that 5%. No model is perfect, and that's exactly why this whole continuous cycle of monitoring and retraining is so absolutely critical. So, there you have it. We went from a meaningless cloud of dots all the way to a tool that could make life-saving predictions. We've seen that the process isn't magic, it's something we can understand. And the potential is just massive. So the real question I want to leave you with is, what problem would you teach a machine to solve?